Okay, first thing I want to give you a warning. We've had some thunderstorms here this morning, including some lightning strikes a fraction of a mile away from our house. And so there's a possibility we may have some interruptions due to lightning strikes, but we'll see. Right now, it's nicer out, but that other storm just came in as kind of a surprise. And we'll have to hope that we just don't get interrupted. Anyway, today I've already clicked record, I'm pretty sure. Um, yes, I did. Okay. We're going to be looking at the effects of relativistic velocities on momentum and possibly some with kinetic energy as well. And as you might guess, something like gamma is going to show up in these things. And so the relativistic momentum, well, our classical momentum, I'll make two columns, I guess. Classical is pre-relativity, and then relativistic. So we'll have some various things on here. Whoops. Classical momentum was just P is equal to mv, just mass times velocity. Relativistic momentum, on the other hand, when something is traveling at high speeds, is that P is equal to gamma mv. So not a huge change to it, although gamma does get big as you have things that are going close to the speed of light. And gamma, well, I'll show you a graph of it here in a minute, but it kind of takes off through the roof. And that's something that happens. And then we'll be talking about relativistic kinetic energy here as well. And actually just relativistic energies in general. Let's see, how should I introduce that idea? Well, there's something called rest energy. And this is an energy something has just by sitting there. And classically, there is no rest energy. But in relativity, the rest energy of something is equal to mc squared. And this is Einstein's famous equation that something has energy just by being if it has mass. And so we've got that. Then there is kinetic energy. Got to hold the pin better. Kinetic energy in classical, it's Ke is just equal to 1/2 mv squared. In special relativity, it looks a little bit different. It actually, Ke is equal to gamma minus 1 times mc squared. And that's kind of different. It doesn't even have the V in there, although the V shows up in the gamma in relativistic energy. And you can actually show that for speeds much less than the speed of light, that you could do a series expansion on gamma. And in fact, we've done a series expansion on gamma minus 1. You can show that it shows up as the regular classical expression when you expand gamma minus 1 in a series and only include the first two terms of the series and so forth. And I've done a bunch of that things. And then there's a total energy. And classically, the total energy is just going to be, it'll be the sum of the rest energy and the kinetic energy. Classically, it's just 1/2 mv squared. But when you add these two together relativistically, you end up with gamma mc squared. And so that's quite a bit different and seems kind of odd that these are things that are going to happen. But let me show you some graphs of these. And let's see, relativistic graphs. We'll just switch over here, the other monitor. Here's a graph of gamma, that relativistic correction factor. And for low speeds, gamma is just about 1, even up to 2/10 of the speed of light. It's not a whole lot different from 1. But as you approach the speed of light, gamma approaches infinity. Okay, we've only haven't gotten all that close to the speed of light, maybe 99% of the speed of light, and it's up over 7. But you go 99.9% of the speed of light or 99.99 and things like that, and it starts getting very big very fast. And there are particles in nature that are going significant fractions of the speed of light, and then we can accelerate them to those rates in particle accelerators, and we can do experiments to test these. So let's take a look at momentum. Classically, the momentum just depends on the speed, and it would be a nice linear graph, which is what I've got illustrated on this thing as dots and dashes on here. And that's the classical prediction, which has been proven wrong. It doesn't work when particles are going 60 or 70 or 80 or 90% of the speed of light, or even closer to the speed of light. The relativistic prediction has been confirmed, and so that works. And then kinetic energy. The classical prediction is actually, classical prediction should be kind of a, well, actually on this scale, you can't even tell that it's a parabola, but it's because it's 1/2 mv squared, it should be parabolic, but I've got such a cramped vertical scale on this thing that you can't even see that. But the relativistic prediction is that it's a curve like this, and goes through the roof, and that has been confirmed as well. So we're going to have to practice using some of these things. Some of the things we'll use are that momentum is conserved in collisions, and so MV or P initial will equal P final, but we may have to include a gamma in there when we're dealing with these things. So I'll come back to this thing, the visualizer, and see which of these expressions we have to use. Momentum is a vector quantity, but a lot of the problems we're going to do with this are going to be one-dimensional. And so our vector nature of it is just going to have a plus or minus sign on some things. So there is it's actually in the chapter after relativity when they start studying photons. They look at a two-dimensional collision that takes place. And what it is there's an electron that's in an atom. So I'll just put a little minus. No, that's not a very good minus sign. Anyway, an electron that's around an atom. Now, at the quantum mechanical level, electrons act like waves and they spread out around the atom. But when you do an experiment that might detect the location of the electron, suddenly that electron wave collapses into a point in space. But along comes, this is a really lousy drawing, but this is supposed to represent an X-ray photon that strikes this electron. And an X-ray photon will have an energy of tens of thousands of electron volts. And so the binding energy of an electron in an atom is a whole lot less than that. for one of the outermost electrons. So this thing almost acts like a free electron. And after the collision, the electron is going to get knocked in one direction, and the gamma ray particle gets knocked in another direction. And there'll be angles on here. So this could be theta top, and this could be theta bottom, or something like that, or theta and phi, whatever you want to use. This is actually going to be the direction that a bouncing off photon is going to have. And because this incoming photon, the X-ray photon, gave energy to the electron, this one is going to have less energy than the incoming electron or incoming photon. And when they studied this experiment, it was studied by, let's see, Arthur Compton was the physicist who studied this. He observed the wavelength change of the photon, and a different wavelength is a different energy, and the angles of everything involved, and often called the Compton experiment. But this is the experiment that finally confirmed for sure. It was the last prediction, really, of Einstein's photoelectric effect theory, which was that light behaves as a particle when it's emitted or absorbed. And this was like the final confirmation of that. And I think Compton got a Nobel Prize for this, for observing this. But anyway, it was a two-dimensional relativistic collision between a photon and an electron. But we're not going to do that. We'll stick with one-dimensional things. So just go with those. But let's start off. A baseball travels with a speed of 43 meters per second. And this would be, let's see, just to quickly figure it out. This would be about 97 miles an hour. So that's a pretty darn good fastball anyway. But by what fraction does its relativistic momentum differ from its classical value? And then in parentheses, I've got, do you sense the need for our favorite series expansion? And I do, because I think we've done something like this. So the relativistic momentum differ from the classical value. Well, here would be the difference between the relativistic value. It would be gamma mv minus mv. And if I divide that by the classical value, something I'd have here, I've got m's and v's all over the place. I'd have gamma times, no, let's take mv times gamma minus 1. There we go. That's better. Over mv. And the mv's divide out, and we end up with gamma minus 1. So that's going to give us the fractional difference between the classical and the relativistic value. And what I need to do is recognize what gamma happens to be. So gamma is 1 over the square root of 1 minus, let's see. Well, we can write this lots of different ways. V squared over C squared, but we've been using some. Beta is equal to V over C, and beta is just that ratio. It's the fraction of the speed of light that something's going. So we could write gamma as 1 over the square root of 1 minus beta squared, which is kind of nice, which we can also think of as 1 minus beta squared. Whoops. The beta squared is supposed to go inside that thing, and this is to the minus 1/2. Okay, so try to correct that, but we're going to have gamma minus 1. However, I can use our favorite series expansion on here, which I'm trying to remember if I've got it on the formula sheet. I should. Oh, yeah. It's over on the back. It's on the last page that has integrals and a few power series for different things. And it's the 1 plus x to the n. So 1 plus x to the n is equal to 1 plus nx plus n times n minus 1 times x squared over 2 factorial. Okay, and then that series just keeps going here, plus dot, dot, dot. X in our case is going to be beta squared, and n, actually it's going to be minus beta squared is what x is equal to for us. And if x is, or yeah, x is minus beta squared, you can see that this changes to 1 plus x. And then our n value for our series is minus 1/2. And I've done this a bunch in these different things. And so the series for us will end up equaling, let's see, we'll have 1 minus beta squared to the minus 1/2 will end up equaling, 1 is the first term, the next term plus minus 1/2. Okay, I'll have that there. And then x is minus beta squared. And then my next term is going to be n, which is minus 1/2 times n minus 1, which is minus 3/2. And x squared is going to be minus beta squared squared. And that's all over 2 factorial, which is just 2. And so anyway, what's that look like? That looks like negative, negative, that's positive. So this would be 3/8 beta to the 4th is what that term happens to be. This would be plus 1/2 beta squared. So, well, actually, I can have the other terms in here, but they're not going to matter. I'll have 1 plus 1/2 beta squared, and then plus 3/8 beta to the 4th, and so forth. Okay, I'm gonna just pull up another piece of paper here and save that bottom problem for, uh, actually, we might have to consider energy on that one, but I think that's all still visible. For us, beta is going to be V over C, and that's going to be 43.0 meters per second over 3.00 times 10 to the 8th meters per second. That's the speed of light. And this is going to be a pretty small number. Okay, 1.43 times 10 to the minus 7th. Okay, so what this series expansion, I'm going to store that on my computer so I don't have to keep track of it too much. Where the heck is, there it is. Okay, let's just write out this series as it should be. 1 minus beta squared to the minus 1/2 is going to equal 1 plus 1/2 beta squared. I'll just square that and stick a 1/2 on it. And I'll have first term is going to be 1.03 times 10 to the minus 14th. Actually, that's the second term in the series. So that's not much. And then I'll have 3/8 times beta to the 4th. So let's see. Oops, I wanted to wrap that in parentheses. No, I'll just calculate it. Okay, for this next term, and these are all dimensionless, by the way, because beta is dimensionless. It's a speed over a speed. I would get 1.58 times 10 to the minus 28, okay, which is not much. However, these terms are going to keep dropping by a factor of 10 to the minus 14th about every time we do them. And so, or maybe 10 to the minus 13th. But anyway, they're getting really small really fast. And what we want is gamma minus 1. And so what we've calculated here is gamma. Gamma minus 1 is going to be this thing minus 1. Well, if we subtract 1 off this series, what we're going to get is 1.03 times 10 to the minus 14th plus 1.58 times 10 to the minus 28th and plus a bunch of other things that are even smaller. This is so small compared to that that we're just going to ignore it and just drop it. And this is the fractional difference between the relativistic momentum and the classical momentum for a 97-mile-an-hour baseball pitch. And it's not much. So it is safe to ignore the relativistic correction when you're talking about baseball pitches. They just don't show up. And there was another application of that thing. Now this one, I don't know how to do this without energy, or at least the way that occurs to me immediately is to do this using energy because we have a potential difference of 50,000 volts. The electron will assume it's accelerated from rest across that potential difference. And so it is losing this much potential energy, but that's the amount of kinetic energy it's going to be gaining. So the kinetic energy of this electron is going to equal Q delta V. Okay, that's an expression that's still good relativistically, but I'll have to use possibly something different for the kinetic energy expression from 1/2 mv squared. Well, okay, remember electric potential is potential energy per unit charge. And if you multiply a potential difference by a charge, you get a difference of energy. And so I would have 1.60 times 10 to the minus 19th coulombs, that's 19 up there, times 50,000 joules per coulomb, which is something or other. Whoops, minus 19. I get 8 times 10 to the minus 15th joules. Okay, now it said it was an electron. Okay, an expression that I gave you or wrote down a little while back here for relativistic kinetic energy is gamma minus 1 times mc squared. Well, we need to figure out mc squared for an electron. Okay, in this case, I kind of have it memorized for a rest energy in electron volts, but let's go ahead and do it because this would actually represent 50,000 electron volts of energy. But let's go ahead and calculate the rest energy of an electron. Okay, mc squared is going to equal 9.11 times 10 to the minus 31 kilograms times C 3.00 times 10 to the 8 meters per second and we square that. So let's find out what we've got here. And whatever we get here is going to tell us kind of whether or not we need to consider special relativity for this problem. Because if this is comparable to the rest energy, or maybe larger than it, we might have to do that. So, all right, let's see. 1.11. Okay, and I get that MC squared is equal to 8.20 times 10 to the minus 14th joules. So this is the rest energy is about 10 times what the kinetic energy happens to be. But let's see, we don't have a lot of sig figs on that one. Um, Kinetic energy, the relativistic expression, is equal to gamma minus 1 times mc squared. Oh, actually, yeah. Anyway, gamma minus 1 is going to be pretty small, but we can figure it out. Gamma minus 1 will equal the kinetic energy 8 times 10 to the minus 15th joules divided by the 8.2 times 10 to the minus 14th joules, which is pretty small. And then we can add a 1 onto that. Um, Oops, I made a mistake when I put this thing in here. Um, just clear that. I accidentally put in a positive exponent on that one, which really fouls things up. Okay, I get about 0.098. And that means gamma is going to equal about 1.09, which maybe isn't so insignificant. Let's see. Well, that's okay. By what fraction does its relativistic momentum differ from its classical momentum? Well, we figured out up here that fraction is going to be gamma minus 1. Actually, that is gamma minus 1. That's the fraction by which its um, relativistic momentum differs from its classical momentum. But to do this, I had to stray into uh, relativistic energy territory. And I was hoping to kind of just start with relativistic momentum a little bit more. But still, that's about what is that? I don't know. That's a fraction. That's about a 10% difference for when you accelerate an electron across a potential difference of that much. So it shows up. That's easily noticeable in an experiment. Okay, the non-relativistic expression for the momentum of a particle agrees with experiment if V is much less than C, like for that baseball, For what speed does the use of this equation give an error of 1% and 10%? So really, because the relativistic expression is gamma mv, what we're actually asking is, when is gamma equal to 1.01 and when is gamma equal to 1.10? So that's basically what they're asking. That would, if it's 1.01, you'd have a 1% difference between the relativistic and the classical expression. And if gamma is equal to 1.10, you'd have a 10% difference between the two. So this is the question, when does gamma equal 1.01? Well, let's see. I think we can write this. Gamma is 1 over the square root of 1 minus beta squared. We can solve for beta here. Let's think of this as gamma over 1 and flip both sides. And you would get, this will be something we can use for both parts of this. You'd get the square root of 1 minus beta squared is going to equal 1 over gamma. If I square both sides, I get 1 minus beta squared is equal to 1 over gamma squared. I'm just playing with algebra here, but let's see. Looks to me like beta squared. I'm going to do two algebra steps at once here. Bring the minus beta squared across and bring that back over here. Will equal 1 minus 1 over gamma squared, or beta is going to equal the square root of 1 minus 1 over gamma squared. Well, if gamma is 1.01, I can just plug that into my calculator. So I'd want the square root of 1 minus 1 divided by 1.01 squared. And I get about 0.14. Now remember, beta is equal to V over C, and in this case, it's going to be about 0.14, but that represents a speed of 14% of the speed of light. And if you just toss that in, 0.14 times 3.00 times 10 to the 8th meters per second. And let's see, I think you get 4.2. Well, I'll just do it. 4.2 times 10 to the 7th meters per second. Okay, so that wasn't so bad. Now for part B, we were going to have beta or gamma was equal to 1.10. So I can just redo this calculation with gamma equal to 1.10. So it would be the square root of 1 minus 1 over 1.10 squared, which for this one, I think it's going to be going faster. Yeah, and I get about 0.4, I don't know, well, it says 10.00, so that would work. Anyway, it'd be about 0.417 is the fraction of the speed of light that this thing is going to be going. And if we repeat what we just did, just take this number and multiply it by 3 times 10 to the 8th. We get about 1.24 times 10 to the 8th meters per second. So this is 41.7% of the speed of light. So that's where you'd get a 10% difference. You definitely have to consider the relativistic expression if you're going 40% of the speed of light. You'd be getting a 10% difference. Maybe you could ignore it if you're only going 14% the speed of light, depending on how many significant figures you have. So, okay, this is just some kind of general things. We haven't done any collisions yet. So let's see if we can track down one of those. Well, this looks like just another one. Okay, on the back of this, we've got one. Good one. But show that the speed of an object having a momentum of p and a mass m is v equals that. Somehow we got the speed of light into here, but looks like we're solving for v. And so p is equal to gamma mv, which is going to be mv over the square root of 1 minus v squared over c squared. And we got v's top and bottom. We're just supposed to solve for v. So this is just an algebra problem. So I'd multiply out from underneath by that thing, and I'd have p times the square root of 1 minus v squared over c squared is going to equal mv. And then I would square both sides, I guess, and I'd get p times 1 minus v squared over c squared. That'd be p squared, excuse me, is going to equal m squared v squared. And this is just a little bit of algebra here. So p squared minus, I'm going to bundle this p squared over c squared times v squared equals m squared v squared. Bring this one across, and I'll have p squared is equal to m squared v squared plus p squared over c squared times v squared, which is p squared equals v squared times m squared plus p squared over c squared, and v squared will equal p squared divided by, I think I'm doing this right, m squared plus p squared over c squared. Now, somehow they managed to, oh, looks like they multiplied top and bottom here by c squared over p squared, I think. Yeah, looks like that. And then the top changes into just c squared. Okay, that's what's going on. And the bottom changes into m squared c squared over p squared plus 1. Okay, then you take the square root of both sides, and you get v is equal to c over the square root of MC over P quantity squared plus 1. Yeah, and that's the same expression. We just happen to have it backwards. I'm not sure what the point of that expression was, but it was just doing some algebra with this thing. So that's all. Okay, here's one that sounds a little more fun. An unstable particle at rest breaks into two fragments of unequal mass. The rest mass of the lighter fragment is 2.50 times 10 to the minus 28 kilograms, and the rest mass of the heavier fragment is 1.67 times 10 to the minus 27th kilograms. If the lighter fragment has a speed of 0.893 c after the breakup, what is the speed of the heavier fragment? Well, here's a situation where I'm going to slide this up a little bit so I can just stick a blank white sheet under here, because it may take more than just the little bit of space I allowed myself there to solve this thing. We've got something that's just sitting here, this unstable particle at rest, and the heavier fragment looks like the mass of a proton or neutron. This thing is a bit more than 10% of the mass of the proton or neutron, so I don't know what this particle might be actually, but that's what you have to begin with. And then afterwards, you've got the heavy fragment, and do they call it lighter? Yeah, the light fragment. This one's headed this direction at 0.893 C. This one's heading in that direction at V sub h, the speed of the heavy fragment. There was no momentum to start with, so these two momenta have to be equal in magnitude afterwards. And so we should be able to do this out, figure this out. So afterwards, you can say that the magnitude of this momentum, which will be gamma for the heavy fragment, the mass of the heavy fragment, times V for the heavy fragment, that magnitude will equal this one, which is gamma for the light fragment, the mass of the light fragment, times the speed of the light fragment. And so that's how you have momentum conserved in this case. And the work, we can actually just get a plain old ordinary number for this one, but it's a little complicated because the speed of the heavy fragment is here, but it's also in gamma over here. And we're supposed to solve for the speed of that heavier fragment somehow. So let's see what we can do to maybe fix this a little bit. One thing I can do, because this is just going to be a number, I can divide both sides by the mass of the heavy fragment, which is also just a number. And over here on the left side, I'll have V sub h divided by 1, the square root of 1 minus V sub h over c squared. Okay, because gamma is 1 over the square root of that stuff. And I've got V sub h times gamma. And that will equal gamma for the lighter part, the mass of the lighter part, the speed of the lighter part, divided by the mass of the heavy part. And this is all just a number that we can calculate. In fact, let's go ahead and do it. With a speed of that much, gamma for the lighter fragment is going to equal 1 over the square root of 1 minus 0.893 squared. Okay, this is this is V, but V over C would just equal 0.893. So gamma for that lighter fragment is going to be 2.22. Okay. So it's going at a pretty good clip. Well, 0.893C, that's a pretty large gamma value. So it's going to pack a lot more wallop than the classical expression would predict. Well, 2.22 times as much. Then I can do all the rest of this stuff. So I'll have all of this stuff in parentheses here will equal the 2.22 times the mass of that lighter fragment, 2.50, that's 10 to the minus 28 kilograms times the velocity of the lighter fragment, which is 0.893. And I'm tempted to just take all of this stuff and pull the C outside the parentheses here and just figure out all that junk first. And so all that stuff on the right side there would equal, and we'll just call it beta, or no, not beta, we'll call it alpha, maybe, something like that. And I get about 0.297 C on the right side. And I'm just going to call this alpha for ease in calculating stuff. So I'll have this expression on the left side is equal to alpha, where alpha is that. And then I'll square both sides here. So I'll get V sub h squared over 1 minus V sub h over c squared is going to equal alpha squared. Multiply out from underneath here, and I would get V sub h squared is going to equal alpha squared minus alpha squared times V sub h squared over c squared. Bring this thing back to the other side. So I would then have V sub h squared plus alpha squared V sub h squared over c squared is going to equal alpha squared. And V sub h squared times 1 plus alpha squared over c squared. And actually, since alpha is going to equal 0.297 c squared, the c squareds are going to go away. It's going to equal alpha squared, or, yeah, well, we can just do it. V sub h squared is going to equal alpha squared over 1 plus alpha squared over c squared, or V sub h is going to equal the square root of all this. So it'll equal alpha divided by the square root of 1 plus alpha squared over c squared. Okay, now alpha is 0.297 c. So this is all going to simplify down to 0.297 on top. And I'm going to put the c out over here. And then down here under the square root, I'll have 0.297 c quantity squared divided by c squared, this is actually going to equal 1 or 0.297 squared is what that's going to simplify to. So let's figure out the speed of that heavier fragment. And this was just playing with conservation of momentum stuff and a horrendous amount of algebra. So, and then when we're done with this, we'll see what it would have been if we just used the classical expression. So I'm going to store that in X also. So I don't foul it up. Anyway, that thing divided by this is going at 0.285 times the speed of light. Okay, and all that stuff worked out to be 0.285. So a little bit different. Then we could multiply it by the speed of light and we'd figure that out. But let's see if we can solve this second part if we use non-relativistic momentum expressions for this. So we still have the collision going on here. If it was non-relativistic expressions, we would just drop the gammas out of this equation that I had here. Here was what we used for the relativistic value up here. We had gamma H, MH, VH was equal to gamma light, ML, VL. And the classical expression just wouldn't have the gammas in there. So we'd have the mass of the heavy one, the speed of the heavy one is going to equal the mass of the light one times the speed of the light one. And we were given the speed of the lighter fragment. And actually, because it's in the terms of the speed of light, we should be able to just figure this out. So let's figure out the speed of the heavy fragment. V sub h will just equal m sub L over m sub h times V sub L. So m sub L was 2.50 times 10 to the minus 28 kilograms divided by 1.67 times 10 to the minus 27th kilograms. And then we just multiply by that speed of the lighter fragment, 0.893 C. And I'm going to leave the C as is. I'll just take the 0.893 times that thing. So 0.893 times 0.50. And I get the velocity of the heavier fragment would be about 0.140 times the speed of light. And what did we get over here? We got about twice that speed. Okay, we got about 0.285 C for the speed of the heavier fragment. So quite a large difference between the two values. So it's obvious with a speed like that, you definitely need to use the relativistic expression for solving for the speed of the heavier fragment after the collision, because this is only half of the correct speed. So quite a ways off. Okay, one last thing I was going to show you real quick is that, let's see, somewhere back here in one of these problems, actually, I'm just going to calculate the rest energies of a few protons. First, for an electron, And the mass of the electron is 9.11 times 10 to the minus 31 kilograms. And we already did this, but m sub e c squared was equal to, take that number and multiply it by c squared. I also want to do this for a proton. And I think we've got that in the back of your book. Yeah, I wanted to do these two, a few significant figures anyway. The mass of a proton is 1.6726 times 10 to the minus 27th kilograms. And the mass of a neutron is, wherever it went, 1.6749 times 10 to the minus 27th kilograms. And just calculate each of these things. And then I'm going to convert their masses into mega electron volts. And just for the heck of it, and actually the electron mass 9.1094. Yeah, just so we have the same number of sig figs on all these things. Let's see. And I suppose if I'm doing that, I should probably call C 2.9979 times 10 to the 8th meters per second. So we'll do all of that stuff to the right number of sig figs. First thing I'm going to do is take this and square it and stick it in, store it on my calculator. So all right, got that one. So all I have to do is take this and multiply it by what I've got stored in my calculator. Okay, and for this one, I don't remember what we had before, but I would get 8.1870 times 10 to the minus 14th joules. Okay, but actually, I think I'm just going to do it for this one. I want to show you something. 8.1870 times 10 to the minus 14th joules. And I'm going to multiply that by, let's see, where is it? There we go, magnitude of the charge of an electron. Let's see, 1.6021. Huh, trying to figure this out. Oh, 1 electron volt over 1.602122, 1.6022 times 10 to the minus 19th joules. And what I would get for the thing on the electron there. Whoops. Okay, I'd get a value of 5.1098 times 10 to the 5th electron volts, which happens to be 0.51098 mega electron volts. Okay, and that is the rest energy of an electron in mega electron volts. Here's a way that the mass of the electron is sometimes written. 51098 MeV over C squared. And this combination of units is used in elementary particle physics and nuclear physics when you're talking about the masses of things like protons and neutrons and electrons. You deal with it in MeV over C squared. And you do that because it's so handy to have them in those units, because you're going to have to be taking relativity into account when you're dealing with those masses, that you just switch to a system of units that's a lot more comfortable. And for the proton and neutron, I don't remember them to as many sig figs anymore, but they're around each of them because they're pretty close in mass. They're about 940 MeV over C squared is the rest energy or the mass of a proton or neutron. And I don't remember exactly what they are. They differ in the fourth significant figure, like 939.6 MeV over C squared for maybe the proton, something like that. But that's just a unit of mass that's used in when you're studying nuclear physics and stuff like that. And kind of works out pretty nice that way. What was really weird and took some getting used to was the time unit that we used. My thesis was calculating oscillations of the shape of a nucleus that would occur, and we looked at how those would change in time. And the unit of time we used was a Fermi Fm over C. Now we called it a Fermi, but it's actually a femtometer, but it's 10 to the minus 15th meters divided by the speed of light, 3 times 10 to the 8th meters per second. And it actually ends up being 1/3 times 10 to the minus 23rd seconds. But that's how long it takes a gamma ray to travel from one side of a nucleus to the other. And that was a convenient unit of time for the things that we were studying, because it was gamma rays that, for the most part, carried whatever force was going to be happening. Gamma rays are something that went as fast and as fast as the speed of light, and they only had to travel across the nucleus. So crazy units that you might be using if you go into some of these fields anyway. Okay, we'll stop there. I'm going to make this handout that I was working on here. I'm going to put it up, but it's 10 pages of problems like this, and that's what we'll be doing this week. And then we'll have some review for the final. Tomorrow in class, I'm going to hand out the practice material for the final exam. And I'll also be giving your tests back and other things like that. So we're coming up on the end of the quarter here.